I have the honor and the curse of being the only experimentalist of the session. So let's see if I can, yeah, um, make the job here. When I was asked a title, I gave a very generic title: Novel Phenomena and Perspective in 3D and 5D transition metal compounds. Because I thought that it would leave me the freedom to pick up between cuprates, nickel compounds, or iridates. And as I came closer and prepared my talk, I decided to talk about this topic here, which is about proximity-induced ferromagnetism at the interface between iridium and cobalt compounds. And I hope this is quite interesting. So there are brief outlines. So first, this is maybe something that motivates a bit my interest for that particular compound, which we did some Raman scattering and found some funny signature of a strange metal dynamics here. And then I'll show you a bit more about interface magnetism in this system, which is made of two materials which a priori are not magnetic, and tell you a bit about more recent results that we just put on the archive about how to control electrically this magnetism. I need to acknowledge here the people who actually did the work. So this is actually the work from Arun Jaiswal here at Karlsruhe, which is funded through this quantum science and technology campus of the Trans Frontier European campus here, UCOR, between Karlsruhe, Strasbourg, Freiburg, and Basel. And Dirk Fuchs, who is our home specialist for thin film growth, as well as Kaushik Sen, who's been doing the Raman measurement and is now faculty at the IIT Delhi. We benefited a lot of the TEM installation of the Institute of Nanotechnology at KIT, as well as from the insight of various theory colleagues, Rolf Heid, who is sitting here, Jörg Schmanian, and Robert Eder. Good. So why talking about 5D compounds? I mean, you know this phase diagram, which is a bit old now, not that old. When you start from a simple metal or band insulator and you increase the electronic correlation, you go towards a mode insulating state. And we heard today a lot about the fantastic thing that happens when you have just this strong correlation and how complicated it is already to apprehend from a theoretical point of view. And on this horizontal axis here is the spin-orbit coupling, which also drives metals into funny states and semi-metallic state or topological insulating state. And if you mix up the correlations with the spin-orbit coupling, there's a whole new world that opens. And so the idea here is that the spin-orbit coupling grows with the number of electrons in the system. And so 5D metals like iridium or osmium are great because they have a sizable Coulomb interaction and a spin-orbit coupling, which is strongly increased compared to the 3D metals and become sizable in comparison with the Coulomb interaction. So that's really where this new physics appears. Now, strontium iridates, so these are members of the Rudolfsen-Popper series. So this strontium N+1, iridium N, oxygen 3 N+1. And I think the most famous representant is strontium 2, iridium 04, which is a G-effective 1/2 mode insulator, which has also a pseudo gap and a funny fermiology. The 327 compound is also quite interesting magnetic properties. And the 113 is a bit the embarrassing little brother here. It has this, so this is this N infinity series. So it's a distorted cubic perovskite. As all is the other members of the family. I mean, generally the octahedra here are quite flexible. I mean, they can rotate a lot and modulate the electronic wave functions and the magnetic coupling here. So the properties are generally strongly sensitive to the lattice and to elastic coupling. But the strontium iridate, the 113, happens to be a paramagnetic semimetal, where it has some Dirac points in this electronic structure, which are they're a bit far away from the Fermi level, something like 150 to 200 milli-electron volt away. But still, I mean, the idea that it could be they could be driven to the Fermi level and give rise to a correlated Dirac semimetal. Now, to grow bulk single crystals of this material happen to be quite hard. It requires high temperature, high pressure, so it's much easier to actually grow thin films, to stabilize them on the thin films. But there again, there's a lot of complications related to the actual structure that you manage to stabilize in a thin film. So this took a lot of work to Dirk Fuchs to manage to find the good conditions to grow the actual right phase, to control that phase and the structure of that phase. I'm going to show some examples. So he's doing this with pulse laser deposition. So you basically have a target in a vacuum chamber here in which you control the oxygen atmosphere. You sublimate your target and you deposit it at high temperature on the substrate. So you do this with doing electron diffraction to monitor the layer by layer growth. And we have all set up to look at the reflectivity of X-rays and making reciprocal space mapping to actually structurally characterize those films. And as I'm going to show you, we do also electron microscopy on them. And especially when we start doing new growth, Rutherford backscattering to actually ensure the stoichiometry and the composition of the compound. The oxygen composition, for instance, is very important. So I'm not going to show all the details of the growth and the characterization, but once we grow those materials, we thought we can investigate the charge dynamics with them. And the idea is actually quite simple. We can do inelastic light scattering, so Raman scattering, which is historically something I've been doing for fun. So we have a film of strontium iridate grown here on this dysprosium scandate substrate. Could be another substrate, but happened that it worked quite well with this one. And you can shine some light and with polarized light and analyze the energy distribution of the scattered light. So that's Raman scattering. And what's great is that it tells you about the dynamics of the charge of the system. Not only you can look at the phonons, but you can also look at the electrons. But that's notoriously complicated to do on a thin film because you have a small volume to probe. But now, if you look at the electronic structure calculated by Rolf here, so that's the Fermi surface of the strontium iridate, you see that there are some large open electron, hole pockets here, and the small electron pocket here at the pi over 2 points. And using the selection rules of Raman scattering, you can actually, by carefully choosing the orientation of your polarization, you can probe the dynamics of the charge either at these points of the reciprocal space, which is mostly going to probe the dynamics of the holes, or along the diagonal here, which is mostly going to probe the dynamics of the electrons. So we thought we'll give it a try. These are some spectra that we obtained. So this is the energy as function of the intensity. So the typical Raman spectra looks quite complicated. There's a lot of phonons, but most of them are actually normal phonons with a normal Lorentzian line shape that you can easily subtract. And you get two modes here, which are a bit more annoying because they show a strong asymmetry. And this asymmetry is coming from a coupling of those phonons to a continuum of excitation, and typically an electronic continuum. And most of the time, we know that there is a continuum just by looking at the shape of the phonon, seeing that there's a funnel. But in that case of iridate, with great care, we could actually measure that continuum here. And so we could see it, and we could actually fit it. So once we removed the boring phonons and we just keep those ones, we actually implemented a global routine to fit this, which was widely used, for instance, in the cuprates, where you have to take into account especially the electron-phonon coupling. But here, the novelty was that to make it without making any assumption of the type of dynamics of the electrons. So Jorg wrote us nicely the response function of a non-Fermi liquid in general case. I mean, if you get this alpha component here, if it's 1, you get a Fermi liquid. If it's 1/2, you get a marginal Fermi liquid, and you can use it basically as a fitting parameter using a memory function response formalism, and you can get very, very good fit of those data. And long story short, and what you get out of this is the scattering rate and the effective mass renormalization. And I'm just going to flash here some of the results. First thing is that the exponent that we got for this non-Fermi liquid was between 0.4 and 0.6, so quite close from the marginal Fermi liquid one. which is fun because, of course, you have this flat continuum, which has been also observed in the cuprates and has been one of the motivation to develop the marginal family liquid phenomenology. And the second observation is that the scattering rate we extract from this analysis is strangely close to the Planckian rate, so linear with T. So we don't see any logarithmic corrections here, probably because the renormalized mass that we get is still quite modest, it's a lambda of 3 or something. And something which was also quite interesting is that from this we can get some kind of charge carrier result mobility. So we can see that the electrons are essentially more mobile than the holes, which is something that you can see also in the Hall effect, which is dominated by the electron charge carrier. Okay, so now that's an interesting system, but what made it even more interesting is this work from the group of Hide-Takagi a few years back, that if you confine now this strontium iridate, so you go from a semi-metal, so now you grow a super lattice with strontium iridate and strontium titanate. And when you reduce the dimensionality, also you make very thin layer of strontium iridate sandwiched between strontium titanate, you see that you go from a semi-metal to an insulator, and that insulator happened to be ferromagnetic as well. So there is the proximity to a magnetic phase here, which has been further explored in combination with other 3D compounds, in particular with manganites, and where by introducing some layers of iridate, you can control the magnetic anisotropy in the magnetization of metallic manganites. Or you can even observe an anomalous Hall effect in superlattices. Sorry, that's not strontium here, it's lanthanum strontium. So that's really in the metallic compound. And that's actually the issue, that when you do electrical transport in this kind of materials, where you do have the transport coming from the iridium, but also from the metallic manganites. And so it's a bit hard to disentangle what is coming from the iridium and what is coming from the other layer. And you get similar issues, a very interesting result on strontium rutinates, but the same thing when you do transport, because the strontium rutinate is also metallic, it's a bit hard to know what is really coming from the iridium. So the idea here has been to grow superlattices using lanthanum cobaltate, which is in principle a semiconductor, but if you strain it, so it has a complicated spin configuration, like all cobaltate compounds with low spin, intermediate spin, high spin. And it happens that when you strain this material, you get actually a ferromagnetic insulator with a Curie temperature of about 85 Kelvin. So a nice XMCD, and you can understand the ferromagnetism then in this compound. And what's very important is that it remains insulating. So when it's grown on STO, we try to gate this to really dope it as much as we could, and that's important for after. And we always get a very high resistance of those films, and we never can get those lanthanum cobaltate conducting in a compound. So we actually grew a series of layers using lanthanum cobaltate in contact with strontium iridate. So we see we have atomically sharp surface, that's electron microscope picture, with no interdiffusion either from the titanate or the iridium or from the iridium to the cobaltate. We can fully strain them. So these are reciprocal space maps that shows you that so for 10 monolayers typically, the iridate and the cobaltate layers are fully strained to the substrate, and we actually suppress all those rotations. When we have in-plane rotations, but the out-of-plane rotations are suppressed, and we have really a pseudo-tetragonal unit cell here. And so what we did is to make a whole bar from this to be able to measure the longitudinal and transverse conductivity. And we did 3 types of systems. So the first one, we just have 10 monolayers of strontium iridate on STO with a capping layer to protect it. The second one, we put strontium iridate and lanthanum cobaltate directly in contact. And in the third one, we put between the cobaltate and the iridate a strontium titanate layer to separate them and avoid direct contact. So we looked at the resistivity, and what you can see is that when strontium iridate is alone, you get this semi-metallic behavior. And when you put LCO and separate it from an SEO layer from SiO, you also have the semimetic behavior. So the transport is really dominating here by the iridium layer. But when the lanthanum cobaltate and the strontium iridate are in direct contact, you see an increase of the resistivity. It's still conducting, but it's less conducting. But what's more surprising is if you look at the Hall effect, now if you look at the transverse conductivity, what you see is that when LCO and SEO are not in direct contact, you do have the normal electron-dominated Hall effect. But when LCO and SEO are in direct contact, you do see now a strong hysteresis here that appears and which arises from an anomalous Hall effect, which actually is telling us that the charge carrier in the SEO layer are actually magnetically polarized. So we can look at it as function of temperature, separate the ordinary Hall effect from the anomalous Hall effect one, and we see these beautiful magnetization, essentially magnetization curves, which disappear about 80 Kelvin when the lanthanum cobalt layer become non-magnetic. So there are several origins for the anomalous Hall effect. This can be extrinsic or intrinsic. There's a way to distinguish that. So we basically have to compare the longitudinal conductivity with the transverse one. And this is intrinsic when the transverse conductivity does not depend on the longitudinal one. And so this is what we've been showing here. So that only occurs at low temperature, so below 30 K or something. So the transverse conductivity does not depend on the longitudinal one, which tells us that this is really an intrinsic effect. And the second interesting observation is that if you increase the thickness of the strontium iridate layer, the amplitude of the effect decreases strongly. So that's really an interfacial effect. And last but not least, we can also measure the magnetoresistance. Now we do have a metallic compound, so the magnetoresistance depends on the square of the field, but there's also a component that depends on the magnetization, and that also show a field-dependent hysteretic behavior in the strong coercive field in good agreement with what we've seen from the anomalous Hall effect. We can look at the angular dependence and deduce from that the ferromagnetism is in the strontium iridate layer with the in-plane 110 easy axis. Good. So the question is what happened there? And what we found is that there's actually a charge transfer from the iridium to the cobalt. So more specifically, we can see, so by looking, for instance, at the slope of the Hall effect at high temperature, so above magnetic ordering, we see a change of the slope, which tells us that there's about 5% of an electron which is transferred from the iridium to the lanthanum cobaltate. But we can also do in elemental resolved ILS experiment. So that's pretty much like an X-ray absorption experiment. So you can look at the cobalt edge, but you can look at it with atomic resolution. And when you do that, you can basically deduce that the valence of the cobalt at the interface has been changed, and it's confirmed that there is an electron transfer from the iridium to the cobalt, which is consistent also with the increase of the resistivity of the iridium layer. So there is this charge transfer. And this was actually investigated theoretically by the group of Tanushree Dasgupta and Sarah Dasgupta in Bangalore. And they also found that if you grow this kind of interface with the cobalt iridium cobalt interface, you do have a transfer of charge across this interface. So you actually dope the cobaltate. So it doesn't make the cobalt layer conducting. The only thing is that, of course, when they calculate this, they actually found that the iridium layer, when you distort it, ferromagnetic, you make the tetragonal distortion or stabilize the pseudo-tetragonal phase of the iridium layer, they actually find that this layer was actually ferromagnetic, which is not something that we have. Because you really need to have it in contact with the cobaltate layer. But the reason why they found that this was magnetic is actually because when you strain the compound, you drive actually two degenerate Weil points here below the Fermi level. So you actually have two file points with different chirality that are driven below the Fermi level. And so when you look at the Berry curvature and you integrate the Berry curvature here, they estimate that this should give rise to an anomalous Hall effect of 7 microohm centimeter, which is about twice what we observe experimentally. So this is in quite good agreement. So I have no idea of the time I've been talking, and I hope I'm still on time. 3 minutes, so that's perfect. The next step, actually, having found that, then we thought, well, we should try to actually get our device, and so this was a bit of work, and to make some gatings of them, and to try to dope the iridium layer by field effect. So when we do that, well, we can estimate roughly the change with like 50 volts of a very modest change of the relative charge carrier density. Yet when we look at the anomalous Hall effect here that we see, you see this nice hysteresis curve, you see that this strongly depends on the applied electric field. And actually, from -50 to 50 volts, we have an increase of almost an order of magnitude of the amplitude of the anomalous Hall effect. So both of the saturation value here at high field or of the coercitive field. And the same thing goes with the magnetoresistance. So this very modest change of the charge carrier density is a very strong increase of the anomalous Hall effect. And that's pretty much my last slide. You can see that the effect is strongly asymmetric. So it's not the same to make a positive or a negative gating here, because you don't start from 0, so it's not centered at 0. And you see that the onset of the temperature of the magnetism doesn't depend really on the applied field. And so if you put this together with the calculation that tells you that the Weil points in the tetragonally distorted strontium data are actually quite close from the Fermi level, so only 10 milli-electron volt away or something like that. You can see why when you increase the charge carrier density, so you move away your Fermi level, you can go across some of those peak in the Berry curvature, and because the anomalous Hall effect is going to depend on the integral of the Berry curvature, you will have a certain increase of the anomalous Hall effect. Good. So in the summary, so we found this interesting magnetism at the interface between two materials which in the bulk state are not magnetically ordered. So it's really an interesting new physics going on from the both the combined effect of strain and confinement of an interface of these materials. And there's a proximity-induced magnetization in the conductive layer of strontium iridate at the interface with ferromagnetic insulating lanthanum cobaltate that we can control by electric field gating. And I thank you for your attention.